All right, let's practice some of these trig identity problems. It's like trig algebra stuff. And I've got my cheat sheet of formulas right here. The main focus is these Pythagoreans, which come in different forms. They just give us these formulas, but of course, this one could be flipped around, shuffled around to be sine squared x equals 1 minus cosine squared x. So not only do we have to look out for cosine squared plus sine squared, we got to look out for these things like 1 minus cosine squared or 1 minus sine squared. We got to look out for that pattern. And additionally, we could break this down even more. It could be 1 minus cosine, 1 plus cosine. So we'll frequently see just, these, the binomial not squared. And sometimes we'll have to give ourselves that second binomial, multiply them till we get this, then we replace it back to sine squared. So we have to be aware of those same variations for these other two. So this thing could be rearranged as, let's see, tan squared equals secant squared x minus 1. And then this could be broken up into secant x minus 1, secant x plus 1. So if I see any of these things, like if I just see this in some problem, that kind of raises my suspicion that it's probably some Pythagorean deal. All right. Okay, let's skim some of these problems and let's practice some pattern recognition. Right away, I see I call it a Pythagorean pair, tan secant. I know those guys, they appear in one of those Pythagorean equations, which is this one. Well, yeah, that one over there. So I don't know how it's going to work out, but a strong suspicion I'm going to have to use some Pythagorean stuff. I'll probably end up multiplying by tan x minus secant x. I'm not sure yet. I have to confirm that's the way it's going to go, but probably. All right, so we're not going to do it. We're just going to scan for patterns like that one. Let's see the next one. So this one, I don't see any Pythagorean-y stuff. Almost looks like a 1 minus cosine. Maybe that'll come up later. But I see some fractions. So I'm going to have to get a common denominator. That's not like a trig thing. It's just an algebra thing. I know I probably want to combine those. So the common denominator would be cosine, which means I have to multiply top and bottom by cosine. And then those will add up, and oh look, I see some Pythagorean coming up after that. Yeah. So in these problems, sometimes they give you two fractions. Maybe this could have been secant or something, or something else, and you need to add them together. But there's other times where they give you a single fraction, like maybe something like that could be broken up. So this, in some other hypothetical problem, this could be broken up into. So usually, you got to do the opposite of whatever they gave you. Also, sometimes they give you problems that they're factored. So maybe it's like that. I'll just make up some random stuff. If it's factored like that, you probably want to multiply it out. But the opposite's also true. If they give you one that's multiplied out, maybe it looks like sine cosecant or something. If they give you something like that, you probably want to factor it. Not always, but... All right, let's keep going. Scan these problems for patterns. So that one, the pattern was add the two fractions. All right, what do you see? I see some obvious Pythagorean right there. And it's got a binomial, and it's a squared, so definitely some Pythagorean. I'm looking at 27. I don't see any Pythagorean. I don't see any fractions to add. So kind of one of our other primary solution methods. Let's see, we got Pythagorean and then add fractions, but the other one is convert everything into sine and cosine. And that's probably how this one's going to go. So right. I want to warn you, don't always do that. Any of these problems, you could instantly turn everything to sine and cosine. Any one of these trig problems, that might be an attractive option. Like, oh, let me just turn everything to sines and cosines. But you don't want to take that bait. You don't want to do that as your primary method of solutions. You want to start with Pythagorean and algebraic simplification. Right, so cosecant is 1 over sine, and secant is 1 over cosine. And then you'll flip and multiply, and that one will work out easy. Scan some other ones. No Pythagorean, no fractions, so you're probably going to have to go sines and cosines for that one. Sines and cosines. This one's pretty distinct. We haven't talked about this, but there's a section of the cheat sheet with negative x's. So that's not a very hidden formula. When you've got a negative angle and a positive angle, you're going to use one of those. All right. So this one, we're going to add the two fractions with common denominator, and you can also see the Pythagorean in there, which after we do the common denominator is definitely going to turn into a Pythagorean squared binomial, something like that. All right, so here, a little more subtle, but I see a squared in the top hinting at Pythagorean. I see this binomial suggesting Pythagorean. So, but it's not squared. Otherwise, I would just turn that into cosine. But I can make it squared by giving it its conjugate. Let me get. Now all of a sudden the denominator turns into cosine squared. This top, I'll just leave it factored. Because I kind of foresee that this thing's going to cancel. Yeah, and it actually, yeah, that's cosine squared. So that's my final answer. Just pattern recognition. So keep an eye out for those binomials and direct your attention to Pythagorean. So verify the identity. So you get to pick either side. Looks like they chose the right side. My instinct would have led me to the left side. You're supposed to usually choose the more complicated side. So when you're comparing left and right, probably do that one. But so let's see what they did. So these two guys don't appear in a Pythagorean, and there's no fractions to add. So I guess you're probably going to just convert this into sines and cosines. I don't know if that's what they did. What did they do? Okay, it took me like 3 minutes to figure out what are they even talking about. I paused it. So this is formatted terribly. It's totally not clear what they're doing. But they are working the left side of the equation. So normally you'd write it and you keep it in a line. So 3 over sine x. Yeah, like I said, when you're doing these, you get to choose one side. So you usually choose the more complicated side, because it's easier to simplify something complicated than it is to like unsimplify something simple. So we'll choose the more complicated side. And you just kind of blindly work it. You just do whatever you can do. Sometimes you gotta take a guess and do 3 steps, and then it doesn't work out, so you go back to the beginning. But this one, we're just going to add these 2 fractions, which means we need a common denominator. At least that's what they did. So cosecant, and this one's sine over sine. So we get 3 cosecant x over cosecant x sine x minus 3 sine. And since this is going to have the same denominator, I'll just go ahead and skip that step and make it one big fraction. So this, I guess this is what they mean here. They're skip 2 steps, I think, and they got to this. So they want you to, this should be sine x. And this whole thing should have been down here. It should be below. You should be working one side and go like this. and just leave the right side the same. And then the next step would be, let's see, what are they doing here? So now they're going to multiply these two things, which turns into 1. Or you could even show more steps. Cosecant is 1 over sine. 1 over sine times sine is 1. So I guess that's what they want you to write here, is just 1. And there's the answer. But the better way to do that one is just, if you're good at this, you just know that turns into 3 cosecant x. All right, this is basically 3 times 1 over sine. 1 over sine is cosecant x. And then 1 over cosecant x is just 3 sine x. So it seems like it should just be a one-step problem. All right. Yeah, this looks like exactly the same thing. So I'm going to let you work this one out. It's still formatted terribly. When I first looked at it, I thought this was some kind of manipulation of the right side. But no, they're manipulating the left side. And they're getting a common denominator there. And they're skipping 2 steps. You might write this out separately and do the common denominator. Let's fill it in there. All right, so here we're up to another identity. Not Pythagorean. If it's your first time seeing this, you probably wouldn't recognize it, but it's pretty distinct. There's a pi over 2 minus theta. Let's go back to our cheat sheet, or a formula sheet, which you should print out, or you probably have your own better version. So that's these guys, which this cheat sheet's not very good in this section, and it doesn't even have tangent, which is the one we want. But it's going to be tan. I guess because the pattern is always the same, they felt it was okay to just leave some out. So this equals the opposite function's cotangent of x. You might verify that on your cheat sheet. And these are called co-function properties. So sine and cosine are co-functions. Cosine and secant are reciprocal functions. Okay. So I think we just said this thing turns into cotangent. And then so I guess that's that. And cotangent turns into 1 over tangent. And then 1. So that looks potentially Pythagorean-y. Tangent and secant do appear together in one of the Pythagoreans. But it could also be a sine and cosine thing. So maybe you try both. And when I say sine and cosine thing, I mean like you could convert this into sine over cosine and convert this one into, what, 1 over cosine. So I think I would try that first. Oh boy. So it looks like we're going to have to do some factoring. I think this is our first one where we're going to have to factor. So we choose either side. They both look pretty much the same. So I'll just choose the right side. Oh, well, they chose for us. They chose the left side. And they're factoring out of GCF. So I'm going to let you take care of that one. Definitely some Pythagorean there. Looks pretty easy. And since there's so many trig functions, that's definitely a sine and cosine deal. Convert everything to some version of sine and cosine. All right, let me know if there's any questions. I'm going to cap it there. All right. I guess I'm going to look at a couple more, because on your Miro page, there's a bunch of these examples that we looked at. These guys. And these These are pretty handy because it's questions and solutions. And the key to these problems is a lot of experience, right? There's not just one process for these problems. Not one set of instructions. Everyone's different. So no matter how good you are, you probably won't be able to figure out all of them, but experience counts a lot. It starts to get easier. And we want to focus on that pattern recognition. So I think I'll skim through a couple more. And I'd encourage you to go check these out. Practice. All right, so these ones, see how there's a lot of variation. There's a bunch of different trig functions. That usually points to converting everything into sines and cosines. Like secant is 1 over cosine, etc. Cosine, cotangent's cosine over sine. And you can see that's what they do in the solution. So I think all of these are going to be like that. They all have too many trig functions. And, okay, so let's look at some other ones. So, all right. So here, what do we see? I don't see any squareds. I don't see any binomials, but I see 2 fractions. We're going to get a common denominator and add them together and see what happens. We probably will end up converting this into some version of sine or cosine. Okay, same thing, add the fractions, common denominator, add the fractions. So these ones, if they give it to you factored, you're probably going to want to distribute. And the opposite's true also. If they give it to you, if you can factor, you probably want to factor. And if it's not factored, you probably want it multiplied. All right. And as usual, the answers are all here, so you can kind of check out how they did it. Number 31. So, 31, 31, 31 down here. So they factored it, Pythagorean, and then switch to up, and let's just cancel to 1. All right. And then I guess this bottom thing, they're just restating the original problem. Saying they proved it. All right. So probably going to distribute that one. Probably going to factor this one, but I don't see anything that factors. So I guess in that case, convert everything to sines and cosines. Multiply this. Okay, and then this looks like they start getting hairy. But this one, my first instinct would be to factor, I guess, a cosine and a sine to the 1/2 out. This one, I don't see any Pythagorean, I don't see any fractions to add, so probably convert to sine and cosine. And this one, I think I would actually try to work the right side. But you might have to trial and error. So these are getting a little thicker, they're getting a little harder. Common denominator and add the fractions, I guess. Actually, it looks like those just, that turns into cotangent, that turns into tangent. Okay, this looks crazy, but stick to the plan. If it's fractions, you're probably just going to go with a common denominator and just hope for the best. Who knows what that's going to look like. This one also, you're probably just going to do a common denominator. All right. Let's just read that one, 30. Let's go over here. Okay, I was scouting around, but I guess I don't have the answers for that one. These ones, I guess I don't have the answers in here. These are just practice problems with no answers. So I've got a few sets. These ones have answers, and I guess here's another set where these have answers. So I'll just randomly look at 48. So we would probably do a common denominator. So let's see what they did. So work the left side. And what? Okay, so they skipped some steps, or did they? So they they multiplied this one top and bottom by secant x plus 1. So they were treating it more in the Pythagorean-y rather than go straight to the common denominator. That makes sense. This is what they focused their attention on. Said, okay, we can give ourselves a secant x plus 1, top and bottom. And then the bottom turned into tan squared. So it's probably all downhill from there. All right. Okay, that's it. I think we got some experience with looking for patterns like factor or add fractions or Pythagorean binomials, or convert everything to sine and cosine.